All right. All right, we have our next presentation.
Today I'm going to talk about our paper, Optimal Location Query in Root Network Databases. This is a collaborative work with Professor Xiaohui Xiao from Nanyang Technological University and Professor Fei Li from our department. So, optimal location query considers three sets of points: a set of facilities, a set of clients, and a set of candidate locations. It asks for a location P, such as a facility built on P can optimize a certain cost metric, which is defined on the distance between the facility and the client. In our paper, we consider this query on the root network. In this scenario, both facility and the client reside on the edge of the root network. And the candidate set instead of a point can be a set of edges, which are highlighted here. The distance between any point is defined as the length of the source path between those 2 points. Let's look at an example. Suppose we want to build a facility to attract as many clients as possible. So in this scenario, if client C is nearest the facility is F, here is F2, then we call C is attracted by F, or F is attractor of C. And the distance between these 2 points is called the tracker distance of this client. In this case, the square, blue square is the answer. It can attract the 3 clients here, which is a large number of clients can be attracted by a facility built on any location along those candidate edges. Of course, the answer could be a line segment instead of a set of points, because you can notice that any facility built on any location along that red segment can attract those 3 clients. There are several related work in the literature. Cabello and Wu deal with a competitive location query in L2 space, which is a variant of the optimal location query. And Du and Zhang invested a competitive and min-sum location queries in L1 space, respectively. However, none of the solutions here are applicable if the facility and the client reside on the root network. So in our paper, we invested 3 variants of the optimal location queries on the root network. The first one is called a competitive location query. Here, the set CP is a set of clients can be attracted by a facility built on P. And this query asks for a location to maximize the number of the clients can be attracted by a facility built on P. The previous example is exactly an instance for this query. And we can also find many applications in practice. Here, example, suppose we have a supermarket and residential locations in a city. Julie wanted to open a new supermarket that can attract as many customers as possible. The second variant is called a min-sum location query. It asks for a location to minimize the sum of the tracker distance for all the clients. Here is an example. Suppose June owns a set of pizza shops that deliver to a set of places in a city. He looks for a location to add another pizza shop to minimize the average distance from the place to their respective nearest shop. The third variant is called min-max location query. It asks for a location to minimize the maximum tracker distance in the client set. For example, given the set of existing fire stations and buildings in a city, the government may seek a candidate location that minimizes the maximum distance from any building to its nearest fire station. We propose a unified framework for all these 3 variants. In a nutshell, our solution works as follows. First, we divide the edges into smaller intervals here, such that all the facility and the client will fall on the endpoint of the intervals. Then we traverse the intervals in a certain order. For each interval, we identify the local optimal locations. The global optimal location can be returned once we confirm that the best local optima found so far is better than the if all the unweighted intervals cannot provide a better solution than the best local optima found so far. So we can return that local optima as the global optima. In the following, first I will introduce how we compute the local optima location for the competitive location theories. So our solution is built on the following lemma. If a client C is attracted by a point on the candidate edges, if and only if there exists an entry here in the attraction set of the endpoint V, such as the distance between C and V plus distance between VP is less equal than the attractor distance of C. Here, the attraction set for endpoint V consists of a collection of entry, which is the client it can attract it and the distance between the client and this vertex. So here I use an example to illustrate the idea of this lemma. Suppose we have edge VR, and the CF like this. And if we want to find a point on the edge to attract client C, then the point should reside on the red line segment. Otherwise, the client C will be attracted by the facility F. So based on this lemma, we have an algorithm for the local optimal locations. Here I just use an example to illustrate the algorithm. Suppose we have an edge with length 5, and the tractor distance for all clients is 5. And the AVR and AVR are the attraction set for the endpoint VL and VR. Our solution starts by creating a one-dimensional plan. And for each client in the attraction set, we draw a line segment to represent the possible location that can attract this client. Here we go. And second step, we scan through all the line segments and find the intervals that maximize the number of the line segment. Here is the interval from 0 to 1 and from 4 to 5. And return them as the local optima also from edge E. So next, before we can execute this algorithm, we need two inputs. This is the tractor distance for each client, and the attraction set for the endpoint of the candidate intervals. So for computing the tractor distance, we use in the Ervig and Huygens algorithm, which is used to derive the Voronoi diagram on the root network. Specifically, it takes the root network and the set of cities as input, and it gradually expands until all the clients are met. For computing the attraction set, we propose two methods, namely the Blossom and on the fly algorithm. The Blossom algorithm is very simple. For each client, we apply a Dijkstra algorithm on the client to traverse the vertex in a ascending order of their distance to this client. So the complexity is here, and the space consumption is big O n squared. For large n, it's prohibitive. So we propose another algorithm on the fly to reduce the space overhead. So a natural way to avoid this space overhead is to not to store all the attraction set. So a straightforward way is to we apply the adversarial algorithm to scan all the vertex starting at V. So whenever we encounter a vertex, client, and if the distance is less than the tractor distance of the client, we add the client to the tracking set of V. But such a solution will incur significant computation cost because we can only stop when we see all the clients. So can we do better? This lemma gives us some hint. So given two vertex V prime, such as the distance is larger than the distance from V prime to its nearest facility, then for any client in the traction set of V, the source path from V to C must not go through V prime. So what does this lemma mean? Suppose we have such a root network which consists of three subgraphs, G1, G2, and G3, and connected by as this. Suppose we want to calculate the traction set for V. Then the lemma claims that we don't need to look into the subset G2 and G3. Why? Because any path from V to the client in the subgraph G2 and G3 must go through V prime and attracted by F prime. So we can ignore them at all. So based on this lemma, we developed this on-the-fly algorithm. Suppose we want to calculate the traction set for V2. So we apply the adversarial algorithm on V2, and when a client is encountered, and the distance is less equal to the tracker distance for this client, then we can add it to the traction set. If a normal vertex is encountered, and if the distance between V2 and V1 is larger than the distance from this vertex to its nearest facility, then we can stop expand from this vertex. So in following, we just keep expanding until none of the vertex can be reached from V2. This is the complexity of the algorithm. So once we find the local optima, we can enumerate the local optima to find the global optima. But such a solution will incur significant overhead when the candidate edge is large. So to address this issue, so we propose a fine-grained partitioning technique to avoid the exhaustive search on the candidate edge. So it works as follows. We first divided the root network into subgraphs. And for each subgraph, we derive upper bounds, which is the number of the clients can be attracted for each subgraph. Then we examine the subgraph in a descending order of their upper bounds. And we can determine if the local optima found so far is larger than the upper bound of all the unweighted subgraphs. Here comes the experiment part. So for each type of this curate, we examine two approaches, the basic approach and the FG approach. For each approach, we test two techniques for deriving the attraction set, the blossom and on the fly. And then we implement all the solution in C++ and run the experiment on the Linux machine with 2 gigahertz CPU and 4 GB memory. And then we use some real data sets, and we derive the 5 minutes. Okay. So yeah, we derive the facility and the client from the building location in these two real data set from OpenStreetMap project. And here is some default setting for our experiment. So I only show some, so just maybe 1 or 2 results for the experiment. First, we vary the number of facilities. As you can see, the Blossom algorithm is quite expensive in terms of the memory consumption. With decrease of number of facilities, it increases dramatically, especially when the number of facilities is less than 1/7 is run out of memory. And in terms of the runtime, the on-the-fly with FGP method outperform all the solutions. So I guess, do I still have time?
Well, yeah.
Yeah.
5 minutes.
The second experiment, we investigate the scalability for all solutions. The memory consumption, as you can see, still the on-the-fly, the Blossom-based algorithm need a lot of memory consumption, while the on-the-fly based algorithm just increase slightly. In terms of the runtime, the Blossom based algorithm just works fine before it runs out of memory. And still the on-fly with the FGP method has the best scalability. So to conclude my talk, we define 3 variants for the optimal location queries on the root network, and introduce a unified framework to address all this type of queries efficiently. And notice that our solution also can work when the client have a weight. Here, we just assume the weight is 1 for all the clients. And this is the future work. Okay, thank you for listening to my talk. Any question?
The weights took away my question, so.
Can you go back one slide? Okay, because I didn't finish reading the future.
Okay.
So I do have a question. Just want to clarify myself. I guess when you're looking for attractors, that you base it off of an attractor distance. Is the attractor distance just you just select the distance yourself, or is there some general way of trying to estimate it based on, given all of these clients and facilities, you can't pick an attractor distance really big because they'll be closer to something. Is it like the minimum physical distance, or?
First, we assume that some existing facility on the root network.
Right. Okay.
We look for another new facility.
Right. Okay.
And then we, for the attractor distance, we pre-compute the attractor distance. As
right.
we mentioned,
okay.
We have 2.
So it's got to be based on it's got to be at least closer than the facility already exists.
Yeah.
Okay. That's what I got. All right. Other questions?
I have a small concern. The fact that you ran out of memory for one of your tests indicates that you were bumping up against the edge of the memory capacity, right? Obviously, for the tests that didn't actually go out of memory. So my question is, did you do this with swap enabled or disabled, because that could severely impact your runtime?
Yeah, we just run experiment. When we say they use a swap, we can stop here. That's why we didn't show
you called it out of memory when the swap started kicking in.
Yeah, we can see that.
Yeah. Yeah. Okay.
All right. Thank you.